Okay, good morning. So I hope you are enjoying your academic, right? So we have already, I think, covered a couple of chapters in your book, probably 3 chapters, I guess. So today I'm going to start a new chapter, uh, which is very, very important. And you might have observed, suppose you are downloading some software, right? Some exe file, right? From some website. So many times you have observed that they write some hexadecimal numbers in the, which is they call it checksum or CRC checksum or something like that, right? So what are these things? Why do they write? So I mean, of course, you know that. So these checksums are written. So basically, to make sure that nobody has tampered the file, right? So suppose in the exe file, if you attach a virus, so this checksum will be different, right? So basically, this is a very, very basic thing. So how do we design these kind of checksums? How do we make sure that, you know, so basically the important aspect. So till now we have looked at security of a message, right? So basically, how do we secure a message, right? And we have talked about ciphers, which will, encrypt the data, and you can, and then you can decrypt and so on. But now we are looking at another important aspects of cryptography, which is, to make sure that message. So for example, this is just one application. Like you're downloading a file, and you want to make sure that the person who is allowing it you to download, he has given you one pure file, right? So nobody has tempered the file, right, from that server, whatever public server he may upload it, right? So now, so basically, so message authentication is very, very important aspect. Also many times, uh, you know when you uh, when you give a instruction to your bank to transfer money to some another person, right? And so these instructions also, how the bank will know that you are who actually sending these instructions, right? So this verification or message authentication is a very, very important thing, right? So basically, we are going to talk about these. So normally, as I in the first example, as I said, that we need to look at, so these checksums are some sort of functions, and we call them hash functions, hash values. So, so today I'm going to talk about, I'll give you some brief mathematical ideas about these hash functions. How do we think about them? What kind of hash functions are good, right? I mean, good means beautiful, obviously. That that you are sure that it is secure. So basically, we'll talk about the security of hash functions as well, and then I'm going to analyze the security using your friend. Who is your friend? Probability. Okay. So using probability, you can analyze these things, right? So that is what is all we are going to look at today. So basically, in these topics, so we have already done, I mean, some of the stuff from the basic symmetric key cryptography. We talked about classical cryptography. So this portion, message integrity, is what we are going to look at. I'm not going to do everything here, but few things. Uh, I remember this is syllabus I had taken from the Stanford, right? So some modifications will be there in the syllabus, right? You will see that. Okay. So so integrity is, message integrity is very, very important thing. So to begin with, so you might have come across MD4, MD5, message digest 4, message digest 5, or these family of hash functions SHA1, SHA2, SHA3. So these are all used for data integrity. So I'm going to focus later on in the next class probably about SHA3. Okay. So today I'm going to build the basic mathematical stuff. How do we think about them? Okay. So as I mentioned, these are hash functions. So basically, suppose I have some bits x1, x2, x3, xn, right? And I want to send these bits to some other person. And if there is a attack which is known as bit flipping attack, somebody may flip the bits, right? So that function will be different, right? So this is a kind of attack. So how do you prevent these kind of attacks, right? So, or I mean, we are not preventing, but actually we want to make sure that nobody has tampered the data, right? So that is our important thing. So what we do, so some data is there, suppose x. We try to find a function which is h, which is known as hash function, and we compute y is equal to h of x. So x is our message. You apply h of x, that is y, and this is known as hash function, right? Or also known as fingerprint, or also known as digest, message digest, MD, message digest or fingerprint. Message is there, and you do the hash value, apply the hash function, and that thing is known as message digest or fingerprint. Okay. So normally I will show you towards the end of the lecture that 160 bits or 256 bits are good. I mean, they are secure. If you go less than that, then you are basically, it's not good thing. Okay. So the secure hash function can be designed. So at least the minimum bits are 160 or 256 bits, something like that, in that range. Okay. So one important thing that, so basically whenever we are publishing a file, for example, so x is our message and y is h of x, and we send this pair, okay, on an insecure channel. Okay. So then if you receive, so you download a file x, then you just compute the checksum, right? So if x has been altered, so x becomes x prime, the hash function h of x prime you compute, it will differ from y, right? So you will able to catch that somebody has tampered the data, right? So this is something very basic thing. So basically the basic structure is x is a message, you compute a hash function y, which is h of x, and send this pair on an insecure channel. User will download both file as well as the hash function. So if file has been tampered, if it is not tampered, you compute the hash function, it matches with y. That means there is no tamper, everything is intact. You can download the file, you can use the file. But if file has been tampered, so this x will change to x prime, some other thing, and then you compute the hash function, it will not match with y. So y is a kind of fingerprint of the data, right, which you are sending with the actual message. Okay, y is also sent along the message. Now, hash functions can be of two kind. One which is based on key, another one which is keyless. Okay, so when there is no key, or maybe a single key, you can say. Okay, so normally we have keyed hash functions. So that means there is a different hash function for each possible key. Okay, and a key hash function is known as MAC, message authentication code. A keyed hash function, where the hash function has a key, okay, is known as message authentication code, right? So suppose there are two people, ls and bob. Ls is sending and there is a secret key k. So ls is sending some data x. So what he will do, he will actually compute. So if x is a message, h of k is, or h subscript k is hash function based on key k. Okay, so h of k of x you compute. So this is known as authentication tag or tag, which is based on key. Okay, and then you send basically this pair x comma y. X is your message, y is a hash function hk of x. Okay, and so you send this over insecure channel, and then once you receive, or you download the file, you check you compute hk of x. If it differ from y, that means it has been tampered. If not, then you can use the file. Okay. Any question at this point? So there are two kind of hash functions. One which is based on key, another one keyless, or just use one key, single key. Okay. This is the basic difference. So formally now, as a mathematician, we should always do mathematical formulation. So here is a mathematical formulation. We can call hash family. So it is basically a 4-tuple X set of possible messages. Now set of possible messages could be finite or infinite. Okay. X is set of possible messages. Y, a finite set of possible message digests or authentication tags or tags. Y is set of possible message digests, Okay. K is the key space. And for every K in K, there is a hash function HK in H from X to Y. Okay. I mean, this is very common. As I mentioned, size of X is either finite or infinite. The message space could be finite or infinite. But size of Y is always finite. Okay. Now there are some conditions. If size of X is finite, message space is finite, and it turns out that size of X is bigger than size of Y. Okay, the message digest is size. So then we call this function as compression function, because we are compressing, right? Message is there, you're computing the hash function, which is number of bits are less, right? So obviously the size will be less, right? So then we say it's a compression function. Okay. Normally we have assumption that size of X is twice the size of Y. This condition we assume, for some reasons which at the moment I'm not going to tell you, but this is the basic machinery. Okay. I think these days people have a lot of mobile phones, right? And they talk, and well, which is okay, right? So people, I see, because the human span, concentration is reducing over the generations, so you cannot focus much. So it's normal thing actually, right? But you see, if you want great success, you need to learn how to focus much anyway. So a unknown key. So basically, okay, a unkeyed hash function is H from X to Y. So this is hash family with one possible key. So that means the size of K key space is 1. So message digest for the output of an unkeyed function. So basically, the output is known as message digest, for an unkeyed function, and it is known as tag for the keyed hash function. Okay, that is a difference in the definition. Now, a pair X comma Y is a valid pair if for H from X to Y, H of X equal to Y. Okay, where H could be keyed or unkeyed hash function, right? It doesn't matter, it could be key based hash function or unkey based hash function. Any question at this point? Yes. Any question? Do you understood everything? What is going on? Anyway. Now we denote set of all functions from X to Y by the set f X comma Y. If size of X is n and size of Y is m, Of course, the size of this will be m raised to power n, right? Any hash family f consisting of functions with domain x and range y is subset of fx comma y. So this is known as n comma m hash family, right? N comma m hash family. These are just notations, or we can call it definitions, so that we can do the probabilistic analysis in a much better way. Okay, so now I'm going to talk about the security of hash function. So we understood this concept that hash function is an important concept, right? And there could be two kinds: key based, without key based, right? And so now the challenge is, how do we design beautiful hash functions, right? And the beautiful hash functions, so basically it depends on, I'm going to describe three problems. One is pre-image problem, second is second pre-image problem, and I forgot which one. It is there anyway. We'll come to it, right? So basically, sometime you don't remember everything. So basically, these three problems are very important. Okay, yeah. Third one is collision resistant. This is very important. Your hash function should be collision resistant. So three properties. If it is difficult to solve these three problems, then our hash function is good. Okay, so how do we define? So suppose h is a function from x to y, which is hash function. So x is a point in x, defined y is equal to h of x, right? So the pre-image problem is, we are given a hash function h from x to y, and y is a point in y. Pre-image is that for such function, we try to find pre-image x in x such that h of x is equal to y, right? So finding a pre-image for a point y in y is a pre-image problem, right? And for a good hash function, this should be difficult to solve, right? Because if you can do it, then you know what to do, right? So this should be difficult to solve, right? So hash function for which pre-image cannot be solved is a one-way hash function, okay? Or it is also known as pre-image resistant. Second problem, second pre-image problem. What is second pre-image problem? So now what is given? A hash function h from x to y and a point x in x. Now see the difference from the previous one. In the previous pre-image problem, y was given and h was given. Y means a point y in y. Here, hash function is there, given, and x is given, right? Now we find another point x prime which is different from x, such that h of x prime is equal to h of x, right? So second pre-image. Okay, so the second pre-image should be difficult to solve. Okay, that's another thing. So hash function for which second pre-image problem cannot be solved efficiently is a second pre-image resistant thing. Now third problem, which is a very important problem, is known as collision. All these numbers 5.1, 5.2, 5.3, I have kept it from the book so that you can match. Okay, I know maybe how many people are reading books? Rarely, right? And this is a very dangerous thing. Warren Buffett has said that you should read 5,000 pages every day. He's reading even today. So if you want to make a lot of money, so basically if you want to make a lot of money, you should have the habit of reading. This is something very important. Anyway, so collision resistant. So what is this problem? So given a hash function h, so only hash function is given. Now find 2 points x and x prime, which are different. Find 2 different points x and x prime in x, such that their hash value is same. Okay, so this is known as collision. Okay, so we want collision resistant hash function, right? So this problem should be difficult to solve. Okay, so this is a very basic thing. Now what we need, the business of probability, right? Probability is a really beautiful thing, and you will observe many, and I think I like couple of things, which are similar to probability. What I'm saying, that so suppose you want to find out some value of some event, So suppose this guy's age, who is sitting here, you want to find from the whole class. So what you can do, ask everyone to vote for his age, right? Tell some number, whatever you feel. And then what happens, you take the average, it will close. Your if size is very high, it will go even more closer, right? So, right? Have you seen these kind of things? Yeah, so it's a beautiful thing, right? Anyway, so now we have to look at so analysis of these problems. Now we are going to look at from the what is known as random oracle method. Okay, this was suggested by these two people, Rogwe and Belar, right? So they have suggested this random oracle model. So, okay, uh, so H is well designed, efficient. When we should be basically from a given X, there should be efficient way to find H of X. So let me give you some details. Actually, there is one example which will tell you that you see that here the hash value of H is known at 2 points, and without evaluating the function, you can find hash value at the third point. So this is dangerous. For example, here H is a function from Zn cross Zn to Zn, is a linear function. And suppose the hash function is h of x comma y is equal to ax plus by mod n. A and b are in Zn, right? Now what? Suppose suppose there are 2 points x1, y1 and x2, y2. At these 2 points, we know the value. H of x1, y1 is z1 and h of x2, y2 is z2, right? Now, if you take two numbers r and s in Zn, you can see that h of this, actually, if you open it, simplify it, it turns out to be linear combination of hash values at point x1, y1 and x2, y2. So essentially, of course, I'm showing you the calculation, but what I'm saying that if you know hash value at x1, y1, if you know hash value at x2, y2, you can just take the linear combination r times this plus s times this, you get the hash value of, at third point, right? So these kind of property, if is there in the hash function, it will be dangerous, right? So we should avoid, right? So we should have hash function which is not having these kind of things, okay? So here is our random oracle model. So how your ideal hash function should look like. So there, it's a very beautiful thing. So they say that in the random oracle model, a hash function h from x to y is chosen randomly from the collection of functions, chosen randomly, and we are only permitted oracle access to the function. Okay, only oracle access to the function. Okay, so the only way to compute hx is to query the oracle. This is the only way. Okay, so look up the so basically we can think of it looking up the value of hx in a giant book of random numbers, such that for every x there is a random there is a complete random value h of x, basically. So basically only random access is allowed, and this is a result which I am not going to prove it, but I am just mentioning it. Suppose h is a random function, so h is a hash function chosen randomly, and x naught is a subset of x. Suppose size of y is m, then suppose that the value hx have been determined by querying the oracle if and only if x is in x naught, right? Then this probability that h of x is equal to y, means we are testing whether it's a hash value, right, is equal to 1 by m for every x in x slash x naught and for all y in y. This is a important result. So basically this probabilistic calculation is, this probability is 1 by m. Okay, so now how many of you have gone to Las Vegas? Oh. Yeah, I have visited twice, but so I'm going to tell you, of course, if you have not gone to Las Vegas, no problem, but we can talk about Las Vegas algorithm. Have you heard of Las Vegas algorithm? So Las Vegas algorithm is a randomized algorithm, It's a beautiful algorithm. So let me talk about it. Algorithm in this random oracle model. So we are going to talk about randomized algorithms. What are randomized algorithms? They can make random choice, okay, during their execution. So they can make random choice. So what happens, for example, in this Las Vegas algorithm, which is a kind of randomized algorithm, is a randomized algorithm that may fail to give an answer. It's okay. It may fail to give an answer. But if, if algorithm does may return an answer, then the answer must be correct. Okay, got the idea? So Las Vegas algorithm. So you will remember this forever, right? Because the name is like that, Las Vegas algorithm, right? So it may fail, but that's okay, right? But if it gives an answer, it must be correct. Now suppose epsilon is a number between 0 and 1, real number. So I am going to talk about two basically probabilities. A randomized algorithm has worst case success probability epsilon. Okay, just kind of definition. A randomized algorithm has worst case success probability epsilon if for every problem instance the algorithm returns a correct answer with probability at least epsilon. Okay, fine. If so, the worst case success probability is epsilon if for every problem instance the algorithm returns a correct answer with probability at least epsilon. And second thing, a randomized algorithm has average case success probability epsilon. That was worst case. This is average case success probability epsilon. If the algorithm returns a correct answer, averaged over all problem instances of a specified size is at least epsilon. Okay. So these are two different things. But so we know worst case success probability and average case success probability. Now we have what is known as epsilon Q algorithm. So epsilon Q algorithm denotes a Las Vegas algorithm with average case success probability epsilon, in which the number of oracle query made by the algorithm is at most Q. So the query allowed is at most Q, okay, to the oracle. So epsilon Q algorithm denotes a Las Vegas algorithm with average case success probability epsilon, in which the number of oracle queries made by the algorithm is at most Q, cannot exceed Q. Okay, so now I'm going to give you, I think, three algorithms we can talk about. First one is point pre-image. Point pre-image. So H is given. Remember, pre-image problem, hash function was given, and a point Y in Y is given, right? And this Q is also given. What is Q? How many queries you can make to the oracle, right? So choose any x naught in subset of x, and suppose the size of x naught is Q. For each x in x naught, if hx is equal to y, then return x. Otherwise, return failure. I mean, this is how very basic algorithm, right? We call it algorithm 5.1. Again, I am keeping the same number as in your book so that you can go back and refer or read something. Okay. Then we can actually compute this number, this theorem, which says that for any x naught to be a subset of x and size of x naught is equal to q, the average case success probability of algorithm 5.1, this pre-image algorithm, is epsilon is equal to 1 minus 1 minus 1 by m raised to power q. Proof is simple, so I am, all simple things I will teach here. All difficult things I will leave it for you, right? That is the best teaching thing. So here, so let y is a fixed thing in y. Let x naught is x1, x2, xq. Okay. Now for each I from 1 to q, ei is the event that h of xi is equal to y. That is this event. Okay. Then probability of this ei will be 1 by m for all I between 1 to q, right? This is from the previous result, right? Theorem 5.1, which I told you. Then probability of ei complement EI complement will be 1 minus 1 by m. What is EI complement means? When HXI is not equal to Y. Okay, that is the complementary event. So this will be, of course, this is the 1 is the whole probability. 1 minus 1 by m is the complementary thing, right? For every I between 1 to Q. Then we can compute. Now see this E1 join E2 join dot 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 E join EQ join, right? And this is meet. So the probability of E1 join E2 join dot 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 join EQ is 1 minus probability of E1 complement meet E2 complement dot 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 meet EQ complement. So this we can compute. Value is 1 minus 1 by m raised to power q. So epsilon value is this. So basically we have this result. Now the second problem is for computing a second pre-image. So so this algorithm goes like this. Okay, hx is assigned to y. Choose x naught is subset of x minus x, and size of x naught is q minus 1. For each x naught in x naught, if hx naught is equal to y, then return x naught, otherwise return failure, right? So this is the second pre-image. And here also, you can compute that for any x naught, subset of x minus x, with size of x naught is equal to q minus 1, the success probability of algorithm 5.2 is this number. So basically, these are important things for you to understand. That's all. I think I will not go. So, ज़्यादा नहीं करना है, right? So, slowly you, right? Okay, so I think, so we have one more class before exam. I hope you are preparing for exam. I have already prepared question number 1, which is quite easy. Okay. So tomorrow, today, just now I am going to Somnath, so maybe we'll design rest of the question paper there. So that's right. So you, okay, so